Okay, thank you for the introduction, Emmanuel. So my name is Andersson Ersman. I work at RISE Research Institutes of Sweden and have been active in the field of organic and printed electronics for the last almost 25 years. So this presentation is entitled Screen Printed Electrochromic Displays. But I will actually also include some work on screen printed organic electrochemical transistors as well, because the motivation is simply that they rely on the same type of materials, so they can be printed simultaneously, and you can also use both devices simultaneously to create more printed electronic systems. So that is the motivation, but the main focus is still the displays. So I already mentioned about the agenda. It will also include a bit on different kinds of substrates and hybrid manufacturing, also including pick and place of silicon-based electronics and so on. And of course, a bit on applications and exploitation. So RISE, we were formerly called Acreo, and then we were only 150 people working strictly within electronics and photonics. Now we are under an umbrella organization called RISE, which is the only research institute in Sweden. So now we're, of course, much more people, 3,000 employees approximately, working with the motto New Solutions for Sustainable Future. And since we are so many people now, we work in a very broad range of scientific research areas. Of course, I'm not involved in all of these, but we are more narrow, working with organic and printed electronics. We also have at RISE a lot of different test and demo facilities. And in Norrköping, Sweden, where I am located, we have something called Printed Electronics Arena, which I will describe. So in Norrköping, we are roughly 30 to 35 people, separated into two units called Print Electronics and Bio and Organic Electronics. We also work for the last, again, 20-25 years in close collaboration with Linköping University. This is, by the way, where I also obtained my PhD degree in organic electronics under supervision of Magnus Bergen, who established this group at this time. And now I think it's probably the world's largest group working with organic electronics. I think there are 150 people at present time. And then we have this common printing lab, Print Electronics Arena, and then we also have a lot of other science parks and business incubators and accelerators and so on. We also have something called HOPE, Home of Organic and Printed Electronics. So the idea is to create innovations at RISE and Linköping University at the Print Electronics Arena, and then you can spin off companies and situate them in this HOPE arena. So Print Electronics Arena, or PIA in short, is where we mostly are working. We have other labs as well, operated by Linköping University, but this is where we mostly do our work. And here we have, I should say, the screen printing is really the workhorse, or the major technology we are using to deposit materials. So we have a bunch of different, we have two semi-automatic deck screen printers with high alignment accuracy and so on, which you need especially when you print multi-layer devices. And we also have an automatic screen printer line called Automatic, but there you really need at least a few hundred sheets to make it worth to set it up. And then we also have a manual screen printing equipment. But then we also have some other things like a couple of inkjet printers, aerosol jet. We also have equipment for coating and lamination. We have laser for patterning different materials and also to cut samples from sheets and rolls. Pick and place for hybrid electronics. And of course also a lot of different curing equipment, photonic curing, heat, UV, and so on. And then we also have equipment for electronic and optical characterization. And I guess most of you are aware of screen printing, which typically is used when you print patterns on t-shirts, for example. You simply have typically a metal screen, aluminum, then you cover it with a mesh, threads. It could be metal wires or polyester wires. And then when you have the mesh, you coat the mesh with an emulsion containing your pattern that you actually want to print. Then you put the substrate on a table and then put the mesh or the screen, and then you put the ink, and then you drag a squeegee to push the ink through the holes in the mesh to create the pattern. If you create multi-layer devices, and let's say you have 5 different layers or 5 different patterns to print, you of course need 5 different screens to create this. Okay, and I guess you know all this as well. So the motivation of print electronics in general, this technology is about depositing insulating, semiconducting, and conducting materials from solution. And by doing this, you can create electronic functionalities on various kinds of flexible substrates, for example, paper and plastics. But you can also reach, for example, conformability, which is important, especially in bioelectronic applications. You can also obtain stretchable and use stretchable substrates. You can also work a lot with cellulose-based materials, both in the inks and also in the substrates, green solvents and so on, to work more towards sustainability. And then also related to bioelectronics, we quite often use organic conjugated polymers. And they are known, most of them are known to be or show mixed ionic and electronic charge transport, which makes them very useful in bioelectronic applications. And about the low cost, some claim print electronics is low cost. I do not really agree, because in academic scales and low scale production, it's actually quite expensive. But of course, once you reach and try to commercialize and reach high manufacturing volumes, then you can really establish a low cost route of print electronic devices. Example research areas, I think you are quite aware of this. Energy, you can create supercaps and batteries. A lot of different sensors are being developed in all research groups all around the world. Medtech and health is huge area. Green electronics, of course, as I already mentioned, on the sustainability with sustainable substrates and green solvents and so on. So about the topic then, organic electrochromic displays. I call them ion-based devices. Could also be called electrolyte-based devices, because they rely on an electrolyte. But they also rely on, in our case, conjugated polymers. So this is our workhorse when it comes to electrochromic displays. This one is called P.PSS. We have at the bottom, you have the P-dot, or the polyethylene dioxide thiophene macromolecule. Here is shown the oxidized state, where you have polarons or bipolarons along the conjugated chains. And these are then stabilized by negative polyanion, in this case, polystyrene sulfonate. And in the middle, you can see the absorption spectra in different oxidation states. So the semi-oxidized is how you typically purchase the inks from, for example, Agfa and Heraeus. So then it's conducting, and it's almost transparent with a tint of blue color. But then you can, if you if you connect an electrochemical cell and apply voltage, you can actually further oxidize it to make it even more conducting and even more transparent. But the most important thing is when you switch it to the reduced state, which then shows this absorption peak at around 640 nanometer. And this is why it appears as a dark blue color. So there you have the electrochromic effect. And this is also reversible, so you can switch it many times. I think we have switched one display for 1.5 million times, and it was still operational, if I remember correctly. So they can really survive for a long time if you drive them in a proper way. You can create them in two different ways. The upper one is called lateral or coplanar. So it's a very simple device. We were manufacturing these roll-to-roll, I think almost 20 years ago. And it's simply based on that you separate two pieces of P.PSS. So they're isolated from each other electronically, and then you simply bridge them by an electrolyte. And then when you apply an electric field or a voltage, the positive side will become further oxidized into its conducting and transparent state, and the negatively biased electrode will become reduced into its blue-colored and semiconducting state. At the bottom, you have a vertical setup, which is almost as simple. The only thing is that either you can laminate these electrodes, laminate the top electrode on top of an electrolyte, or you can also develop overprintable electrolytes. So you print electrolyte and then you print, for example, P.PSS or whatever counter electrode you have on top. And then again, you can switch them back and forth in a reversible manner. Now, one of the most important things here is that if you look around the world for all the different electronic display technologies that exist, most of them, or almost all of them, need some kind of electronic support, some kind of transparent conductor underneath the display material. It's often could be very thin layer of gold or any other metal. But the most important or most commonly used one is maybe transparent conductive oxide, for example, indium tin oxide, which is used in all mobile phones, for example. But this is actually not needed when you have P.PSS, because here we rely on its intrinsic conductivity. So it acts as its own electrode, and it's also electrochromic. So this is a huge advantage. So we can just deposit the P.PSS, and then you have both the electrode and the electrochromic material at the same time. So we have over the years developed this technology. We started with these roll-to-roll lateral devices, as I mentioned, 20 years back. And then we slowly moved to vertically stacked devices by developing these overprintable and UV curable electrolytes. So we can stack them with screen printing. The advantage of of course you can use other techniques too, but the advantage we see with screen printing is that it's really a scalable method, which is suitable for large area electronic components, for example, displays. And this is also what Invisible is using for the manufacturing of their displays. They are licensing our RISE display technology, and they are currently running the roll-to-roll production in Linköping, 30 minutes from our lab in Sweden. So again, screen printing is really scalable production technique. And I'm not sure if you're aware of Invisible, but they are trying to commercialize this. And there are, of course, a bunch of different applications within environmental monitoring, Internet of Things, and so on. And you see a couple of examples at the bottom there. The rightmost image is medical device, and then you have large area signage, parking signs, and shelf labels, and things that you can use in the stores and so on. So there are lots of different applications for this. Yeah, so I already said it's a simple architecture, and you can use either sheet by sheet or roll-to-roll manufacturing by using screen printing. This particular display technology operates in reflective mode, which means that we need a transparent substrate. yeah, so you look at the color change through the substrate, but this is also an advantage because it provides mechanical protection to the whole device, since the outer surface is made of plastic or whatever substrate you're using. And the particular display you're looking at here on the right is segment-based or direct address, which means that if you have, for example, 10 segments, you need actually 11 drive lines, 10 for the segments, one for each segment, and then one for the common ground electrode. I've talked a little bit about substrates. So here's one example of what maybe looks like plastic, but it's actually not. There's a video here as well. I hope you can see it when this one switches. So there you see the switching between oxidized and reduced states. This is actually nanofibrillated cellulose serving as the substrate. So it's a fully all organic device, including even the substrate. So that's really moving towards sustainability. And this was used in a European project. At the bottom right there, you see the whole demonstrator, a drug of abuse biosensor platform. So we had 5 different biosensors detecting 5 different drugs, and then the display was used to indicate the concentration level in saliva or blood. Another option is actually to print on glass, and this maybe you think is not very flexible, but we did this just to show that we could print the whole system on glass. And what you see there is an NFC antenna, and then you have a couple of silicon-based chips to take care of the energy harvesting, and also the microcontroller to read a sensor, which was also printed, and then to update on the electrochromic display. And in fact, glass can actually be flexible as well. If you look at Schott or Corning, they are producing glass with thicknesses clearly less than 100 microns, so they can be used in roll-to-roll production, for example. We can also make stretchable devices. So this is one example of stretchable displays where we put or we deposited also via screen printing all the different display materials or display layers on top of TPU, which you probably know is a very stretchable substrate. And yeah, to the figures to the right there show simply that we didn't see that much of change when you stressed the device or strained it with different percentages. We still obtain the same color contrast, for example. You can also flip the whole structure, and then we don't need a transparent substrate, and that also means that you can actually print everything on a standard cellulose paper substrate. So the leftmost figure here is the standard architecture where you need a transparent substrate, but here we flipped everything. So we used a paper, standard paper, then we printed the counter electrode at the bottom, the electrolyte, and then some insulating layer to define the actual segments or the pixels, and then the electrochromic B.PSS as the final layer. So that's also one option if you really want to use standard paper, for example, as the substrate. So that's clearly possible as well. You can also combine this with what we call vapor phase polymerization, or VPP. So what happens here is that again, all layers are screen printed here, but instead of printing the polymer, the electrochromic polymer, it's vapor phase polymerized instead. So what you do is that you instead screen print a oxidant layer, and then when you put in figure D is supposed to show that you put everything into a chamber containing E dot. This is the monomer, ethylene dioxythiophene. And when the substrate here is exposed to the vapor of E dot, these molecules will attach and polymerize only where you have the oxidant layer. So this means that you can pattern really fine structures in this way by first screen printing the oxidant and then polymerize it in this chamber. And here you can also choose other monomers, of course. So here are some examples of ProDot and polypyrrole, for example. This yellow one is the electrochromic polymer polypyrrole. And by doing this, you can also think of, like we did here at the bottom right, you can mix, you can create blends or mixtures or layered structures and so on by different by stacking different electrochromic polymers, either by adding two monomers at the same time, or we can also do this VPP process several times in a way to create multiple colors and so on. So then we move into addressing, and of course the dream is passive matrix addressing. The main reason is actually that you really minimize the number of I/O pads on the silicon chip used to drive these displays. And if you really have a display with lots of segments or pixels, then it's simply not worth it to use direct addressing. If you look at this inset in figure A, you can see now it's a bit skewed, to be honest, but it's the square here. So if you think of a square-shaped matrix address displays, you see the number of pixels on the x-axis. So 49 is, for example, 7 by 7, and 961 means that you have a square with 31 by 31 pixels. And of course, if you have these black dots, is direct addressing. So if you have 961 pixels, you also need the same amount of drive lines. And today, a display can contain even millions of pixels, and then you can imagine that it's more or less impossible to drive that by direct addressing. So then you need to go towards matrix addressing, because then you split up the display in rows and columns. So for this example here with, for example, 30 by 30 pixels, you need only 60 drive lines instead of almost 1,000. Because then you have 30 rows and 30 columns. But what you need is a well-defined threshold voltage or nonlinear pixel switching response. This is what enables the possibility to use passive matrix addressing. This is actually what you see here when we combine a carbon counter electrode with a certain electrolyte and PEDOT-PSS as the electrochromic material. Then you can see that the reduction onset to the blue state occurs slightly above 1 volt, plus 1 volt, and it's maybe not as well defined in the oxidation direction, but approximately minus 0.5 volt. You have the onset of the oxidative switching back to the transparent state. And you see there's no area dependence. The black and red is 1 square millimeter and 100 square millimeter, and they show the same behavior. Same thing with the number of cycles, from 1 cycle up to 100,000 cycles. They're more or less the same threshold voltage. Again, +1 and -0.5. So it's quite well defined. And when you have such hysteresis, you can also drive them with passive matrix addressing. We can skip this one. I guess it's lagging anyway via Zoom. Okay, so again, here you see also the same kind of hysteresis, but now you have color contrast on the y-axis and voltage on the x-axis. And again, you see the onset of coloration occurs at +1 volt, and the onset of oxidation back to the transparent state is approximately minus 0.5 volt. So then there are different ways to drive these displays. The one here in the image is called V3 protocol. And it's simply because you define a certain voltage V, and which you apply to the column you want to address, and the row that you want to address is put at 0. So this will give you the voltage V. And all other columns are set to 1/3 of V, and all other rows are set to 2/3 of this voltage V, which means that the resulting, all the neighboring pixels you see here will have either plus or minus V3. There are other protocols as well. We have, for example, in the text here, you see it's called the VHAF protocol. And it's almost even more simple. You simply apply VHAF on the addressed column and minus VHAF on the addressed row. And then you put 0 to all other rows and columns. But then you quite often need to skew this anyway, or modulate the amplitudes. So here's one example. Again, I'm showing the same curve where we have this onset at +1 and the and minus 0.5 for the different colorations, which means that these are the threshold voltages that you should be careful about. So in our case, we used our V was 2.4 versus 0. That is the addressed pixel. And then we put to the non-address columns, we put 1 volt, and to the non-address rows 1.4. This gives us minus 0.4 or 1 volt to the neighboring pixels, which is within this hysteresis window. So nothing happens. You will have no crosstalk whatsoever in these pixels because of this voltage hysteresis. These passive matrix displays are as easy to manufacture as the standard rise display. It's just that you separate everything into rows and columns. So it's 6 different steps. You print first silver lines, and this is simply to reduce the overall resistance for the next layer, which is the P dot columns. And then the third layer is an insulating layer defining the cavities for the electrolyte, or actually it defines the pixel area. Layer number 4 is the electrolyte, which is printed down into the cavities, and then you have the rows consisting of printed carbon. And then layer number 6 is again silver to reduce the resistance. So number 1 and 6 here is actually not needed for the functionality. It's more to improve the switching time and so on. So layer 2, 3, 4, and 5 are the critical ones. So again, what you can do with this is see this chess pattern here, and it appears in the video as well. So what we do is, first of all, there is no crosstalk, and then we also show the grayscale imaging, because once you hit the onset of the respective coloration directions, you have a linear coloration or decoloration, which of course means that, for example, for every 100 millivolt you increase, you gradually increase the contrast as well. So you have the possibility to obtain this kind of grayscale imaging. You can also update them in different ways. This is one way where we switch each pixel to its full contrast. So to create the image, you just sweep or scan the rows one time, but you can also grow the image like this, where you shorten the row scanning time, and then you gradually, the image will gradually appear on the screen, on the display. So, and each pixel here is roughly 1.5 by 1.5 millimeter. Yeah, and just one quite fun application for this is fully dynamic QR codes that could be easily read by mobile phone. Yeah, we can skip these videos. Another thing you can do is actually to create a display where you can interact or play with it. For example, for large area signage or even games like the one on the video. So here we created a capacitive touch interface, but it's actually already exists, so there are no extra processing steps needed. Since we rely on the conductivity of the PWPSS in this case, you can hook up a microcontroller and use the capacitive sensing functionality, and then you have created this kind of interaction with the display. So far I've only talked about reflective displays, but there are of course also a desire to create transmissive displays. For example, smart window is a quite huge area, of course, to install such windows in architectures, in buildings and so on. So here's one example where we used two different electrochromic materials. One is called Prussian blue and the other one is again PEDOT-PSS. So what we did was we relied on a substrate based on ITO plus Prussian blue, and then we printed our standard display on top. And PEDOT-PSS was printed as the last layer. And then we could create this electrochromic display operating in transmission mode. And the advantage here is that Prussian blue and PEDOT actually switches in complementary mode, so they switch in different directions. So in one state, both are transparent, and the other state, both are blue colored. So you kind of enhances the coloration effect by doing this. And this is also what we probably will use in a completely new project called Elegance, which actually also involves UNINOVA. So early in the morning, I had a meeting with Emmanuel before this webinar started. So as I said, it's a new project started in November, so we haven't gotten that far yet. But the idea is to create a hybrid stack of light-sensitive either memristors or phototransistors, and on top of this, we also will have transmissive electrochromic structures or pixels, preferably updated by passive matrix addressing. But the challenge here will be to create both the passive matrix addressing and the transmissive part to make it fully printable, and the dimensions will also be extremely tiny. That is the target. So we'll see what happens, but it's a 4-year project, so I hope we can develop some interesting devices. So I also promised to talk a little bit about transistors. So the thing is, they rely on exactly the same materials in the way we print them. It's again PEDOT-PSS and an electrolyte, and then you have PEDOT-PSS again as the gate electrode. So instead of relying on this electrochromic property, you use the fact that the reduced state of PEDOT-PSS is semiconducting and the oxidized state is conducting. So you can switch these devices by many orders of magnitude. Same thing here, you can create both lateral devices on the left and also vertically staggered devices on the right, where you simply stack the gate electrode on top of the electrolyte to, of course, miniaturize everything. The manufacturing is equally simple as well. Here's the one way of creating them. Again, every layer is screen printed, so you print, in this case, first the silver, then you print the PEDOT-PSS channel, then you have carbon as the source drain electrodes, then you have an insulator to minimize parasitic currents, and then you put down the electrolyte and finally print the PEDOT-PSS again, but now as the gate electrode, and that's it. So here's one example of one A4 sheet containing 760 devices, transistor devices. 2 of them were not working, so that gave 99.7% yield, which is quite impressive by using screen printing as the manufacturing method. You see some examples. The bottom figures are the distribution of the on and off currents and on-off ratio and so on. And the upper left here is the transfer curves of 5 of these 760. And as you can see, they are perfectly on top of each other and switching probably 4 orders of magnitude or something like that. Yeah, this just shows that you can create, of course, circuits if you have transistors. So these are examples of inverter structures and NAND gates, logic NAND gates. Can skip this one. Here are a bit more advanced circuits. The left one is a 47 BCD decoder, so where you minimize the number of inputs, but still can address, for example, a 7-segment electrochromic display. To the right here, you see serial in, parallel out, 7-bit shift register, again, to drive a 7-segment display. And this is, of course, an ideal circuit because you only have 2 inputs, one clock signal and one data input. So there you really minimize the number of pads on the silicon chip used to drive these devices. And as I said, since we rely on the same materials in both the electrochromic displays and the transistors, you can actually manufacture them in the same way. If you print one of them, you get the other one for free. So here's one example of monolithic integration of both the 7-segment display and, in this case, a 427 decoder used to drive the display. You can also drive quite high currents through OCTs. So here's one example where we used them. We embedded the similar decoder circuits into a multi-pad electrode, which was brought in contact with the skin, and then you can actually stimulate muscles with this. The human sensory threshold is about 1 milliamp, and we could deliver well beyond this level. Here's one example showing the addressability. So here you can select which pads that are active, and then you stimulate only those, or the tissue only under those actual pads that are selected. And here's the opposite. If you can stimulate muscle, you can also do the opposite in the reverse direction. So here we use same kind of decoder circuits and put the silver electrodes into contact with the skin. And then you can, when you contract your muscles, you generate EMG signals that could be monitored by the OCTs. Here's another example of how we can combine electrochromic displays and transistors. Instead of passive matrix, this is active matrix addressing, where you put one transistor to the left here in series with 1 pixel, and then you can really lock in the charges and prolong the retention time and so on. So that's another way how you can combine PSS, electrolytes and so on into both electrochromic displays and transistors. The transistors can also be printed on stretchable substrates such as TPU. And here I also mentioned before the VPP process. Here's another example where we actually deposited the transistor channel of the OCT by using VPP. And these were really showing high on current levels. The green one here showed almost 100 milliamp at 1 volt. So it was just about 10 ohms in the on state of the transistor channel, and you could still turn it off by 3-4 orders of magnitude. Here's another example to speed up the OCTs. Since it's ion-based, it's relatively slow, but here's one example where we combined aerosol jet printing with screen printing. So we aerosol jet printed the channel and made it as narrow as 15 micrometer, and then we could speed up and get the propagation stage delay in inverter circuits of just 1 millisecond in an all printed OCT-based circuit, which again is very advantageous if you want to use them to drive electrochromic pixels and so on. And I also talked a bit about sustainability. This is a quite recent work where we used green solvent, bio-based and non-toxic, to dissolve the active channel material of an OCT. And this is almost the last slide. I'm just showing, this is a transparent cellulose-based paper where we print a bunch of different sensors. And one example is piezoelectric sensors. And again, this is just, I'm showing this because you can also combine, of course, sensors with electrochromic displays. So here's one example where we implemented or integrated electrochromic displays together with piezoelectric sensors to detect break-in attempts in buildings through the windows and build a whole LoRa network so you can monitor all windows in a building. So now I mainly talked about the advantages. So are there any challenges? Yes, there are. And the main challenge, I would say, is that both the displays and the transistors are very sensitive to humidity fluctuations because the electrolytes are hygroscopic. But you can actually mitigate that by encapsulating the devices between barrier films. You see an example in the graphs here. The upper one is display, where the blue one is stored in dry. So then you completely disable the coloration. And the red and orange here are when you store them in 80-90%. Then you have a lot of parasitic reactions going on instead, and you simply degrade the PEDOT-PSS much quicker. Same thing with transistors. The trans curves, the red one is again when you store it in dry environment, then there is no way to drive it. And here you see also the parasitic effects in the green and blue, while the black one is in normal environment. But all these artifacts can be mitigated by encapsulating the device between barrier films. And you can even print the devices directly onto barrier films. So that's it. In summary, I've tried to cover a bit about our electrolyte-based devices, mainly the electrochromic displays, but also the electrochemical transistors, since they can be used in combination with each other. Yes, I think I stopped it there. I think time is up as well. So thanks a lot for your attention, and thanks to UNINOVA for arranging this INFRACHIP school, and thanks to all the funding agencies.
Thank you very much, Peter. So I think we have one question in the chat. Thank you very much for your presentation. It was quite nice to see so many applications with electrochromics. So the question is, what is the finest resolution pixel transistor size that can be achieved using in this case, the printing techniques? From Ali Azimi.
Okay, if you only talk about screen printing, if you talk about the transistor, there we normally use 80 micrometer channel length and maybe 100 micrometer channel width. Then you can have a very high manufacturing yield. Of course, we have tried smaller, but then you lose in number of functional devices. And regarding electrochromics, I would say it's the same, because if you think about it, the transistor channel is an electrochromic pixel, because once you switch it, you also change the color. So I would say it's about the same dimensions. But then again, in one of the last slides I showed, we combined aerosol jet to print a channel. So that's one way to combine different techniques to really minimize the feature sizes.
Thank you. Now, if there's more questions, I have one question regarding, so you spoke about the driving lines. So when you have the electrochromic pixels, so I think it's quite complex when you have if you have 30 by 30 pixels is one thing, but then if you want to make it printed like something 1000 by 1000, for example, I think is something more tricky and much more complex to make in a roll-to-roll line, for example.
Yeah, exactly. I'm trying to find this curve. Maybe you remember it, but yeah, I mean, it's more or less, I would say, impossible to use this direct addressing technique if you have too many pixels. It's not realistic to have thousands and thousands of IOs on the silicon chip. So there you really need to go towards matrix addressing in one way or the other, either passive matrix or active matrix.
Yeah.
So you define it in rows and columns instead.
There is one more question regarding even here for the people that is hearing. So concerning this, so the printing electrochromics in the transistor. So if you think in the whole printing process of the electrochromic cell and even displays, typically the speeds here are not so high, right? To print the complete display, even by screen printing. So we are speaking like what, 10 meters per minute, something like that, higher.
No, I think it's maybe, yeah, actually, I don't know because we normally use, or we always use sheet to sheet printing nowadays. Invisible is using roll to roll, but I'm not sure about the speed, to be honest. Because I would say what limits is probably not the printing as such, it's more the drying.
Exactly.
Especially for example, PDOT and let's say carbon and silver, which are cured by thermal means. There you have to roll it through the oven in a quite slow manner to really evaporate all the solvents. So that is probably the bottleneck in terms of speed.
So thank you very much, Peter. We need to move on. Thank you for your nice talk. And if someone else have questions, then you can also email Peter about this talk. So thank you very much. So our